let's assume you're a network operator, and one customer calls and complains about poor performance. You start investigating, and you suspect there is some link in a network that is congested. So you start looking at counters on switches and routers, and you actually find that one link is congested. And let's say somehow you find a new configuration that moves some traffic that was going over the congested link to a underutilized part of the network. And then the customer is happy again. But what about tomorrow? Is there, maybe tomorrow the network is in a slightly different state. Maybe some link has failed, and now there is congestion, maybe in another part of the network. Is there a way of ensuring that even in the near future, the network will not experience congestion? This is a problem that recent systems have been looking at, more specifically QArc and U. And the problem that they were trying to solve is, given a network configuration and a traffic matrix, they try to find the worst case link load under arbitrary failures, let's say for up to 2 failures. And they work very well. They are scalable to large networks, but especially in an ISP setting, they are neglecting the fact that the traffic is routed according to BGP routes. And so if those routes change, then the path of the packets also change, which then affects the loads in the network. And so we were asking this question: how much do routing inputs affect the load in the network, especially the maximum load in a network? And so we conducted an experiment. And what we did was we measured so we went through overall link failures, or overall up to 2 link failures, and we measured the additional loads that each link can have in the worst case. And what I'm showing here is a CDF of the additional load on each link normalized by the link's capacity. And we can see here that in the median case, so like, yeah, in the median case, each link has around 20% more load on the link. And so we repeated the same experiment, but this time not only concerning up to 2 link failures, but also up to 10 destinations for which BGP routes can change arbitrarily. And we can find that in this scenario, the worst case load is much higher. So here in the median, we have around 60 to 70% additional load. And it goes up to 130%. So clearly, when you're just considering link failures, you're vastly underestimating worst case loads that you can find in a network. And this is what the previous work has looked at. So the question that we're trying to answer is, given a network configuration and a traffic matrix, we try to find the worst case loads under arbitrary failures and under arbitrary routing changes. And this is a very hard problem. First of all, the space of possible routing inputs is extremely big. So if you just look at one destination, this destination might be advertised from any one of your BGP neighbors. And if your network has, let's say, 30 neighbors, which is on the lower end, I would say, this would already mean that you have to go through 1 billion possible routing inputs. A second challenge is that the failures essentially introduce dependencies between destinations. And what I mean by this is that the worst case failure for one destination is different from a worst case failure of another destination. Or even worse, just for one destination, for one set of routing inputs, the worst case failure might be different than when another set of routing inputs is present. And so this makes it hard to navigate this joint space of failures and routing changes. And the last challenge is that the input space is very big. When you're just looking at failures and not about routing changes, you can build a traffic matrix that just measures the amount of traffic from each ingress link to each egress link. But if we're also looking at the routing changes, you also have to consider the traffic towards all the destinations. And currently in BGP, there are over 1 million destinations advertised. And so the traffic matrix is extremely big. So the input space is very big. These are essentially the two problems that we have. We have a large search space that is hard to navigate, and a large input space. In our paper, we present Velo, which is a system the first system to find worst-case link loads under failures and routing changes. And it solves the two challenges that I've mentioned before with two techniques. First, it reduces the search space, and then it reduces the input size. So let's first look at the search space. The basic idea is that Velo considers each failure separately. And the idea behind that is that within a given failure, we can find the worst case for each destination independently. And once we find those, we can add the resulting links up to get to find the worst case routing inputs. And if we can do so quickly enough, we can go through a lot of failure scenarios still in a reasonable amount of time. But the hard part here is to find the worst case inputs for one destination in one failure quickly enough. So let's look at an example. Here we have a small network. We are looking at one destination that is currently has traffic coming in from 6 different ingress links. And we currently receive 3 equally preferred BGP routes, the orange one on the right. And we're interested in the worst case load of link UV. So as I mentioned before, just going over all of the possible sets of egress of egresses does not scale. Instead, Velo looks at the routing. Let's assume for now that routers always route according to hot potato routing. That means they forward along the shortest path to the nearest egress. And then let's say this is the forwarding state that we end up with. And now let's look at node V. This node V currently selects the egress on the right. But now what we can also see is that all the other nodes that already forward traffic along link UV also select the same egress, the egress on the right. And this is because any subpath of a shortest path is also a shortest path. Now, if let's say we receive a BGP withdraw of that route from the top egress, that cannot change or it cannot decrease the load on link UV, because all the routers that are already forwarding along that link are choosing another egress. So basically, whenever you're removing an egress that is not currently selected by V, the traffic cannot decrease on link UV. It can only stay the same or increase. And what that means is that the worst case is always when there is only a single egress. And we prove that in the paper. We prove it also for different routing protocols that are routing traffic along optimal paths or along paths for which subpaths of optimal paths are still optimal. And we prove that it still holds if you're using ECMP for load balancing. And so what Velo now has to do is it no longer needs to go through all the possible sets of egresses, but just over each egress computes the forwarding state, propagate the load, and then find the resulting loads on the links. So let's say this is the worst case routing inputs, where all the routers select the egress on the right. But this is only for one destination. If we look at a different destination, we have different traffic distribution. So let's say now we have more traffic coming from the ingress at the bottom, from the green ingress. And now the worst case is different. Now the worst case is maybe when the top egress is the only egress available. And so what that means is we still have to go through each destination and find the worst case inputs, and there are still 1 million destinations. And this brings me to the second technique of Velo, which is to reduce the input size. This here is an example of a traffic matrix. We define it such that one row represents all the traffic that is coming in from one ingress link, and one column represents the traffic that is going out to one destination. And so the matrix is extremely wide. It has as many columns as there are destinations, so around 1 million columns. But from the slide before, we know that the worst case state depends on the distribution of traffic. And if two destinations have a similar distribution of traffic, so the similar proportion of traffic that is coming in from all the ingresses, then they will have the same worst-case routing input. There have been measurement studies that have actually shown that this is the case in internet traffic matrices, that a lot of columns are very similar to others. And so we are leveraging this property. Let's consider two destinations here, D1 and D2. Notice that here D1 is roughly 10 times bigger than D2. It's not exactly 10 times bigger, but it's roughly. And what that means is that most likely the worst case routing input is the same. And if it's not the same, then the difference in the resulting load will still be small because they are very similar to each other. The idea of Velo is to then combine these two destinations together into one combined destination, and we just add up the two columns. And by doing that, we make the matrix smaller. So Velo formulates this problem of approximating the matrix by a smaller one. We formulate it as a clustering problem. The problem is that given a number of clusters, let's say 300, find 300 clusters of similar destinations that have similar traffic distributions. And we solve this problem using a modified k-means clustering algorithm. So the output of this clustering is then a much smaller matrix that just has, let's say, 300 different columns. We also prove in the paper that the clustering error that we are computing also bounds the approximation error that we're doing. Because when we're making the traffic matrix smaller, we inevitably will make errors. But the clustering error will guarantee that the actual error, the approximation error that we're doing, is below that threshold. So I've shown to you now these two techniques, the first one to reduce the search space and the second one to reduce the input size. And the first one improves the scalability, while the second one also improves scalability, but at the cost of accuracy. So there are two questions that we should answer. How scalable is Velo, and how accurate are its results? Let's start with the first question. To evaluate the scalability, we run Velo on all of the topologies from Topology Zoo. For instance, on the largest topology, Velo finds the maximum load of all 1,790 links within around 3 hours. And this is over up to 2 simultaneous link failures and 10 routing changes. In this scenario, Velo went through roughly 3 million failure scenarios. That means 300 scenarios per second. And so these numbers were obtained when using 300 clusters. But if you don't use clustering at all, it takes roughly 70 times longer. This here is, again, just with 100,000 destinations. If you use 1 million, it will take roughly 10 times longer. So this shows that Velo is scalable. But how accurate is it? To answer this question, we obtained a real traffic matrix from a research network in Switzerland. And we then run Velo on the original traffic matrix and on the approximated one. And we compare the results to find how accurate the results are. And we find that with just 300 clusters, the approximation error is usually below 0.5%. We also compute the error bounds, which in this case is also usually below 5%. And this is only for 300 clusters. If the operator is interested in more accurate results, they can increase the number of clusters to, let's say, 1,000, and then you get roughly twice accurate results that are almost twice as accurate. We repeat the same experiment, but for synthetic matrices as well, where we change some of the properties of the distribution. For instance, making it more skewed usually results in a more accurate results. And this is nice because in traffic matrices in the real world are heavily skewed. And so this again shows that clustering is a very good fit for this problem. So Velo clearly scales well to large networks, and it's accurate. So what are the open questions? The first problem is that it finds the worst case state, or worst case inputs and failures. But it doesn't mean that this is also an accurate or a likely scenario that will happen in the future. By restricting the number of failures and the number of routing changes, the results are a bit more likely to occur. But still, there are, for instance, destinations that are more stable than others in their routing inputs. Again, Velo allows the operator to specify a set of destinations that do not change, or for which the routing inputs change just slightly in a very restrictive manner. But still, can we use probabilistic techniques to find the most likely routing inputs and failures that cause congestion? A second problem is that the ingress traffic is not constant. Traffic always changes. Of course, you can run Velo multiple times with different matrices that you obtain during various peak times or incidents that you had congestion in the past. But still, can we somehow reason about the worst case traffic shifts and how that affects the worst case load in network? These are two problems that we're currently exploring. So to summarize, I've presented to you Velo, which is the first paper to find the maximum link loads under link failures and routing changes. And it does so by reducing the search space and reducing the input size. And now I'm happy to take questions.